In this video, we'll discuss the Excel solution for the transshipment problem. Right? So here on the bottom right, we have the network. We have two suppliers, one Nebraska, two Colorado, three intermediate transshipment nodes, node 3 Kansas City, node 4 Omaha, node 5 Des Moines. And at the very right, we have three customers, node 6 Chicago, node 7 St. Louis, and node 8 Cincinnati. Okay, on the left, in the gray box, we have the mathematical model. So similar to the transportation problems, we have one variable per arc, right? So for example, for the arc from 1 to 3, we'll define the variable x13, denoting the amount of wheat or amount of grain shipped from the farm in Nebraska to the grain elevator in Kansas City, right? So it had we'll define such a variable for each arc. So there are 1, 2, 3, 4, 5, 6 variables on the left part of the network and 9 variables on the right half of the network. Right? For the objective function, similar to what we have done for the transportation problem, we multiply the unit price, which is shown as the label for each arc, with the associated variable for each arc. So this will give us the cost associated with each arc, which represents a route, right, for the shipment of the wheat, right? And of course, we'll do this for every arc, and then we add them up to get the total cost. Okay. The constraints. So again, there are three types of constraints, right? As what we have seen in the transportation problems, we still have the constraints for the suppliers, the constraints for the customers, but because of the introduction of the intermediate nodes, transshipment nodes, we also have the constraint for them, right? So the first two constraints shows the supply constraints, right? For the Nebraska and Colorado, there's two nodes, right? Same thing as before, whatever is shipped out of each supplier, right? So 1, 3, 1, 4, 1, 5. Okay. In this case, should be equal to 300, right? Should be equal to what they have. So again, because this is a balanced problem. Total demand is 600. Total supply is also 600, right? So we know that each supplier will ship out whatever they have, and each customer will indeed receive what they want, right? And of course, right, if we have an unbalanced problem, then it will be different. We'll have inequalities, but you can refer to the table in the slides, which will tell you what type of constraint you should use. Okay, but for this particular problem, we have equalities. For each customer is the same again, right? We are looking at the incoming arcs. We add up the associated variables for the incoming arcs, and it should be equal to the demand, right? For the transshipment nodes, we look at both the incoming arcs and the outgoing arcs, right? So here we assume that whatever is received by each transshipment node will eventually be shipped out to the customers. So the total number that goes into a transshipment node, like for example here, will be x13 plus x23, should be equal to the total number that that is shipped out of the node, right? x36 plus 37 plus 38, right? And of course here this is the standard form of the constraint, right? By moving what we have for the out, initially they're on the right hand side of the constraint, to the left. But technically it's equal to say that we have x13 plus x23 equals x36 plus x37 plus x38, right? So these two equations are basically the same, right? Okay. Okay, so now let's take a look at the actual implementation of the mathematical model. So as you can see here, we had 4 tables, right? So actually what we did is to break this network into 2 parts, okay? So we will solve the left part, which is in the green box, using the above the 2 tables at the top, and then we'll solve the right half of the network in the purple box using the 2 tables at the bottom, right? So we'll first take a look. So essentially we're converting this transshipment problem into 2 subproblems, and these 2 subproblems are actually transportation problems, right? Okay, so let's focus on the left half in the green box, right? So we have Nebraska and Colorado, right, being the supplier, and Kansas City, Omaha, and Des Moines being the transshipment nodes. But in this subproblem, they can be regarded as the customers, right? Okay. All right. So same thing as before, right? We want to calculate the total cost, right, for this left half, okay, for this sub network, right? So it would just be a sum product of the variables and the unit shipping cost, which is stored in the separate table, right, from column I to column L, right? So it's 0 now because we have empty blue cells, right? And empty cells will automatically be regarded as 0 by Excel. So the value, right, that we get by evaluating this formula is going to be 0, right? Okay, and then we have those yellow cells, right? Again, so these 2 yellow cells in column E should calculate the total grain shipped out of the 2 farms from Nebraska and Colorado. So again, we're going to do a sum over the variables associated with the outgoing arcs, right, in the network. Right? But in terms of the spreadsheet, it would just be the 3 blue cells on the left of the yellow cell. Right? Same thing for this. Okay, and they should be equal to the actual supply numbers, 300. Okay, and then the 2 cells in light yellow in row number 8 should compute or implement the function that calculates, right, the amount received by each grain elevator, right? So for Kansas City, it would be the sum of x13 and x23, right? For Omaha, it will be x14 plus x24. For Des Moines, x15 plus x25. Right? That's in the network. But if we get to the spreadsheet, it will actually just be the sum of the 2 blue cells that are above the yellow cell. Okay? And here it will be sum of C6 and C7. This will be D7 and D6. Okay, so all of them will be evaluated to 0, again, because we have empty blue cells. Okay, so we finished the left half, right, the sub-network in the green box. So now let's get into the network in the purple box, right? So again, we define 9 variables, 1 variable per arc. There are 9 of them, so 9 blue cells, right? And we want to calculate the total cost in the cell in light orange. So same thing as before. It will be the sum product between the variables and the unit shipping cost, which is also stored in a separate table on the right. Okay. And the yellow cells will again be used to calculate the number or the amount of wheat or grain. Right? For the 3 yellow cells in column E would be the amount of grain shipped from each grain elevator. Right? And we're going to look at, so remember, we only consider the sub network in the purple box, right? So the 3 yellow cells in column E should calculate the total amount of grain shipped from the 3 grain elevators from Kansas City, Alma, and Des Moines. Right. Going back to the spreadsheet, it would just be the sum of the 3 blue cells. Same row on the left of the yellow cell. Right. Oops. Copy and paste it. Right. B14, D14, B15, D15. Okay. And here, right, this 3 yellow cells, okay, should calculate the amount of grain received by each customer, by each flour mill. Right. So we're going to look at the incoming arcs. Right. So again, we can also look at the mathematical model. It would be the sum of, should be here, right, the sum of some variables, right, with the same J subscript. Right, so there are 2 subscript I and J. I is the from location, J is the to location. Right. So getting back to the spreadsheet, it would just be the sum of the 3 blue cells that are above the yellow cell. The sum C13 through C15. Sum D13 through D15. Right. Okay, so these 3 cells are the in for the transshipment nodes, right? Tons received at elevator, that is the transshipment nodes. These are the out, okay, of each transshipment node. So this should be set to equal, right? So these 3 yellow cells should be equal to these 3 yellow cells if we're going to add the constraint to the solver. Right? So in here, just to make it a little bit easy to understand, we created a separate, we created 3 additional cells used just to reference, as a reference to whatever we have from the 3 yellow cells in row number 8, right? So eventually they should be set to equal. All right, so now we have all the formulas ready. We go to the data tab, click on the solver. Okay, let me erase everything first. Okay, so we have the objective being the orange cell. Right, so this is, oh, sorry, I think I forgot to put the total cost, which would be the sum of these 2 light orange cells. Okay, right, so this is the cost for the network, sub-network in the green box. This is the cost for the sub-network in the purple box. The sum of these 2 will give us the total cost. Right? Okay. Objective is G8. We want to minimize the total cost. The variable cells are this and all the blue cells. So B6 through D7 and B13 through D15. Okay, constraints. So first of all, oops, this 2 should be equal to 300, which are in column G. Okay, and these are the supply constraints, and we also have the customer constraint These three cells should be equal to 200, 100, and 300. And lastly, we have the transshipment node, transshipment constraint. Right? And we check this box to make sure that we have non-negative results. Use simplex LP as the method. And we click on solve. Let's keep the original, let's keep the optimal solution. Right, so this will be the optimal, right? So the total minimum shipping cost would be 12,400, and these are the amounts that are shipped from the farms to the elevators, from the elevators to the flour mills.